Hello, my name is Aditay Rana and here is my project video for the course of ELL. The topic that we are going to discuss today is about resonance in LCR circuit. First of all, the term resonance describes the phenomenon of increased amplitude that occurs when the frequency of a periodically applied force is equal to or close to the natural frequency of the system on which it acts. Electrical resonance occurs in an electric circuit at a particular resonant frequency when the impedance of circuit elements cancel each other out. Here is RLC circuit with some basic information. Here we plotted the graph of 1 upon V versus frequency, which gives Lorentzian curve. The peak of this graph occurs at resonant frequency, which is equal to 1 upon 2 pi into root LC. Characteristics and uses of series resonance circuit. Some basic information about series resonance circuit. Here are some graphs plotted for the series resonance circuit. We can observe that at resonant frequency, impedance achieves its minimum value, whereas current circuit achieves its maximum value. Characteristics and uses of parallel resonance circuit. Here are the effects of resonance on electric circuits. The phenomena of resonance are used in a wide variety of applications in electronics. Some of the more common applications are as following. Applications of resonance in daily life. Resonant circuits have a variety of applications. For example, in the tuning mechanism of a radio or a TV set, the antenna of a radio accepts signals from many broadcasting stations. The signals picked up in the antenna acts as a source in the tuning circuit of the radio. So, the circuit can be driven at many frequencies. But to hear one particular radio station, we tune the radio. In tuning, we vary the capacitance of a capacitor in the tuning circuit such that the resonant frequency of the circuit becomes nearly equal to the frequency of the radio signal received. When this happens, the amplitude of the current with the frequency of the signal of the particular radio station in the circuit is maximum. Let us try to understand the concept of radio tuning. When a lot of people speak together, hardly we can make out anything, but a radio can. Even though it continues to receive hundreds of different radio signals, we can make it listen to any particular channel. Well, the question is, how does it do that? The solution lies simply. Radios have something that we don't, LCR circuit. Let's see how it uses the resonance to tune into specific channel. On plotting the graph between current and frequency, we observe that if we just change the frequency, the current will change dramatically. If the frequency is very low or very high from the graph, we saw that the current is very tiny. But if the supply frequency equals to the resonant frequency, resonance occurs. This is when the impedance of the current becomes minimum and the current goes haywire. The important thing to understand is that different radio stations get broadcasted at different frequencies. Let's assume that there are channel A and channel B with R1 and R2 as their broadcasting frequencies respectively. Let's assume that at given R2 frequency, the radio antenna is observing the radio waves of both the channels. As a result, the antenna vibrates with both the frequencies, and what an antenna does is basically converts radio signals into electrical signals. So, because of these two, the antenna is trying to drive our LCR circuit at both these frequencies. But look from the graph, we can see that all the messages that are coming from R2 is able to generate much larger current from channel B as compared to channel A. And as a result, very high current of channel B grows through the speaker, whereas low current from channel A will hardly drive the speaker. Now, if we want to switch to channel A, we need to reduce the resonant frequency of our LCR circuit, which can be done by increasing the inductance or increasing the capacitance. Different radios have different methods, but generally capacitance method is more common. When we turn the knob, the distance between the capacitors changes and therefore capacitance also changes. Therefore, by increasing the capacitance, the resonant frequency would start shifting towards left. So by this, we can switch to channel A. Here also everything remains same as previous case, with one difference that frequency is turned to R1 and channel A currents are more higher considerable than channel B currents. Let's take a case where we increase the value of resistance. The resonant frequency remains same. Therefore, peak value is observed at the same resonant frequency, but change in current is observed. the peak value of the current would be smaller and therefore the new graph is somewhat flat as compared to the original one. It also has consequences. Here at a given frequency, the difference between both the currents of both the channels is so small that it will not be able to recognize the correct channel. Therefore, the message gets mixed up, whereas previously the difference was much higher, so at that time there was no such problem. Therefore, we can say that previous graph had higher quality of selecting the frequency and rejecting everything else, but this graph has lower quality. Hereby, we can conclude that quality is inversely proportional to the value of the resistance.